We're going to do our unit test for this probably Tuesday next week would be my guess. It's a straightforward one. It's not meant to be tricky. But we've talked about the idea of animal anatomy and physiology, the idea that cells make up tissues, tissues make up organs, organ make up organ systems, and that leads to organisms. That leads to you. We talked about the difference between anatomy and physiology. What's the difference between anatomy and physiology? I get up and move around. I can't take this sitting. I'm sitting all day for some reason. Anatomy. What's anatomy? You talk about something's anatomy. You're talking about its... Sorry? Function, sure. And just the... Do you want to get that door, Sarah? It's super loud out there. Is this what teaching across the hall from me is like? Just somebody yabbering? Okay, you're supposed to be like, no, Orlando. It's like a... Sorry? I do shut my door. It's true. Try to be considerate, you know. When we talk about anatomy, we're talking, about function, but really about the parts, too. Like, what the parts of the body are and what they do, right? And we talk about physiology. It's really related. It's like, how do those things work? What is actually going on, like kind of the nuts and the bolts of it? Does that make sense? To give a comparison, anatomy would be like knowing the parts of a car and like what they do. And then physiology would be like knowing it at like the mechanics level. How does it work? How are these put together? Maybe even at the engineer's level. Like, how does this thing really function? Does that make sense? And we talked first about the circulatory system, right? Like, how does that work? And that was one you would have talked about in grade 10, but we went into a bit more detail, right? We looked kind of specifically at the chambers of the heart. Did you do that in grade 10? Look at the specific chambers of the heart. So we did, right? And we talked about blood flow through arteries away from the heart, through veins back to the heart into capillary beds. We talked about blood pressure, right? Which is a physiology piece, right? That because the heart is a pump that works by contracting, we talked about the fact that when the heart is contracting, it's under high pressure. We call that systole, or the systolic pressure. And then when the heart is relaxed, we call that diastole, or the diastolic pressure, right? And it's still under pressure. The pressure until you die doesn't drop down to zero, but it goes up and down. So we talked about all that. Then we talked specifically about the blood as part of that system, right? And we looked at blood kind of in greater detail. We talked about blood typing, and we talked about the heart in its sort of specific detail. By the way, the first thing you're going to do tomorrow, which is something I've been meaning to do a few times, and I've been such a train wreck this semester. I genuinely apologize for my incredible... Do you know that normally my claim to fame in my first 9 years of teaching, do you know how many days I missed? 0. The answer is 0. Day comes because that's something I want you to know. We talked about the respiratory system and the different parts there and how it works. We talked then about some physiology again, like, okay, how do the lungs actually work? So we built lungs. That was fun. I found that fun. But we also looked at like measuring breathing. Does anyone remember what the machine we measured this with is called? S word. Spirometer? Spirometer. What's going on here? What's happening while this graph is going between like what looks like 0 and maybe negative, I don't know, what would we say that is? Is that 0.6 maybe? Sorry? Regular breathing. And if we know how this goes, the first thing this person does, are they breathing out or breathing in? Yeah. I mean, it's as much a guess as anything. The one thing I'd say is, when we do a deep breath in or a deep breath out, which one can go further? Feels like a lot. What about all the way? A lot more, right? Does that make sense? So that breath out can be a good hint to you if you don't know which way to read the graph. If we go up above and down below normal, we have a lot more room below. There's a lot more air to get out of our lungs than we have space to put in when we kind of hyperinflate. The other thing you could use is with this particular model, negative means out and positive means in. Does that make sense? So the thing just starts reading at 0, and if you start and then breathe out, it's going to go down to the negatives, and when you breathe in, it'll go more positive. So how big is a normal breath for this person, roughly? I don't expect you to read this perfectly, but if you had to call that something, what would you call it?
Negative 0.5.
Yeah, 0.5. I think it's a bit past. I'd probably say 0.6, but I'd accept 0.5. That's fine. Of course, negative is just direction in this case, right? We're not breathing in negative air. Spend too much time around some people, you'll be breathing in negative air. You know who I'm talking about. Yeah. Um, and then how much air can we breathe in if we do a deep breath in? If that's kind of our normal spot, well, we said that's about 0.5, that's about another 0.5. So a deep breath in could be a whole liter of air. And if you picture like a 1 liter bottle, that's a substantial amount of air, right? What about then when we do a deep breath out? Half a liter, almost 3/4, 1/3 of a liter, 1 3/4, 2 3/4, 3 3/4. That's probably about 4 liters of a full breath. That's like 2 2-liter pop bottles of air. It's a lot of air, right? You should know the names for these things. We have them here. I'll leave that to your reading. We talked about the digestive system, which this should really have been mostly review from grade 10. Did this feel like mostly review from grade 10? Yeah, probably, which is why we went at it pretty quickly. We probably went into a bit more detail. You probably didn't talk about like cell types and about villi and microvilli in the large intestine in grade 10, though maybe you did. Depends on your teacher. And we talked a bit more about purpose, I think. And we talked about the nervous system. And we said that the purpose of the nervous system is to do what? Why do we have a nervous system? Sorry? That's right. To make sense, yeah, that's exactly right. So to see the environment around you and then to respond to it, to regulate it. In other words, to help us kind of regulate our things. Do me a favor, close that for me, please. So for example, it's cold outside. We can detect low temperature. We can light a fire and the temperature increases. This is basically what we do, only instead of doing external things like lighting a fire, it's talking about things that happen in our body. Mind you, if you light a fire, that's still your body doing it. So that actually still involves your nervous system. And we said the part of your brain that does the regulating, the thinking, the decision-making, the controlling, all of that is what we call our central nervous system. And where do we find that? Well, the whole brain. Your brain is central. The brain stem, and down the spinal column is a whole bunch of central nervous system. Because some things don't actually have to go to your brain. Remember, you touch something hot, your hand just pulls away. What do we call that? A reflex. That doesn't go to your brain. That actually, there's just control centers built into your spinal column to make it even quicker, just for fast responses. But it's still your central nervous system. Yeah. Could just be damage. In general, your nerves aren't supposed to lose sensitivity over time if undamaged, but of course we do lots of things to damage them, right? And then the actual parts that do the sensing and the actual things that control the moving directly, we call that our peripheral nervous system. These are like the wiring, basically, that collects information and gets it to the central nervous system, and then that gets the information from the central nervous system and actually does the doing. So we call that the peripheral nervous system. And we talked about neurons. We talked about how they have this side which collects signals of an electrical nature. These look like little tree branches, so we call these the trees. But of course we call them the trees in Latin, so we don't call them the trees, we call them the dendrites. And then this looks just like a big straight tube, so we call it the big straight tube. But of course we call it the big straight line-shaped tube in Latin, so we don't call it the big long straight tube, we call it the axon, like axis, right? Think Y and X axes, just big straight line. So straight part, put it down, you'll be okay. You'll be okay, put that. No, over here, away from you. Watch, okay, over here. You're gonna be okay. It's okay, you'll survive. You'll survive even being bored by me, and I'm very boring, I get it, but you'll be okay. You're tough. I know this about you, honesty. Very tough. That look you're giving right now, it's a tough look. And we talked about how some of these are designed just to receive information. Some are involved in these circuits that actually make decisions, just like a computer. And then some send signals back to control things. All right, and we looked at a couple examples. Today we're going to look at another system called the endocrine system. And this system also is about regulating responses. All right? So like the nervous system, the endocrine system helps to control body systems. I'm just going to say organ systems rather. I don't know why I said body organ systems, just organ systems. Instead of using nerves to send electrical signals, does anyone know what your endocrine system uses? Yeah, very good. I'm just going to put ES for endocrine system, because I don't want to write endocrine 6 million times. The endocrine system puts chemicals called hormones Hello.
How's it going?
I'm doing well, thanks. How are you?
Do you teach period 4?
I do not.
You do not?
Nope.
I'm trying to. I know you're.
No, it's all good. What's up?
I'm trying to. My computer was always able to connect remotely to a projector in my class over there, and now it just won't anymore.
Okay.
I wonder if there's something I can do with it, or.
Yeah. Okay. So I mean, it could just be that the receiver needs to project. Have you tried straight depowering? Like, is it one of the little wireless projectors that says like Microsoft press Windows K on the screen, that kind of thing?
Yeah.
Yeah. Have you tried unplugging that thing and plugging it back, and waiting like a minute, plugging it back in?
Okay. So
That's first line of defense. And if that's still not working, let me know. But often it just needs a power cycle.
I believe that the other teacher that's in there.
Yeah.
Is able to still.
Yeah, even still, sometimes power cycling it could be some driver operation.
Is doing some funny.
Yeah, there's some driver weirdness, and then if that doesn't help, then I'll come take a look and figure it out.
Yeah. I've been trying to figure it out. I can't. So.
Yeah. Okay. Power cycle everything. Like, do a full shutdown on your computer, wait a minute, turn it on. Do a full unplug on that, wait a minute, plug it in, and then that often, like 90% of the time, that's all I will do. Yep. And if that doesn't do it, then we'll take a look at other things. Yeah. Is that cool?
Yeah, that's good.
Cool. Yeah, just let me know.
Okay.
So, no problem. And yes, this is me shamelessly checking my cheat note, which I even more shamelessly modified from one of these and then forgot to. Oh, for God's sakes. That is. Okay, what did I say? How's it work? Okay, cleanse. Yeah, okay. For shame. Okay, so how does it work? Again, you're seeing how the sausage is made here, because usually I hide this on my desk. So how's the endocrine system work? And the short version is hormones are released by organs called what? What organs release hormones? Put away. Oh, put away. Are you writing this down, my friend? Are you doing it digitally? Do you have your computer? You normally type them, do you not? No. You're okay? All right. So hormones are released by organs called what? Hello? Hello? Yes. They move through the bloodstream and are designed to interact with proteins in the cells of certain organs called hormone receptors. This allows a single signal, try saying that 5 times fast, to affect many, many cells at once. So when your brain sends an electrical signal down a nerve, the only thing it's going to affect is the other end of that nerve. So if it's on a muscle, it will affect that muscle, or if it's sending it to your eyes or whatever. But with a hormone, it gets released in your blood, and it can tell a whole bunch of cells to react at once. Does that make sense? So the advantage of that is, say we want to send the signal, whoa, we're about to, like, there's a bear over there. It's coming right at us. What do we want basically all of our systems to start doing? Yeah, so what things do we want to turn on? We want to get our muscles going, right? We want the mitochondria of our muscles to just start firing like crazy, right? What else do we want to turn on so it gets going? If there's a bear and we might have to run, we might have to fight it, we might have to wrestle it, right? Yeah, right? That's the hormone. And think about the adrenaline response. What happens when adrenaline kicks in? Right? Your heart starts to beat faster, right? You start to sweat, right? Because we want to make sure we're not going to overheat, even though we're going to move a lot, yeah? That's right. What we want to turn off, we want to turn off some of those pain receptors, right? That makes sense. We basically shut our digestive system down for the moment. We're like, hey, we don't need that right now. Let's settle down to it, right? You get into like what we call fight or flight mode, right? Which is you amp up a whole bunch of systems and you shut a bunch of unessential systems down. Makes sense, right? And we don't want to have to send a million individual signals. So we have, this thing called adrenaline or epinephrine that we send out, and it sends the message, hey, time to do that, right? So just gonna do a little bit more cheating again. Which row did I do this in? Key glands, yeah, glands, and then I actually want to, okay, we'll do that. Okay, so the hypothalamus is a region of the brain. I'm going to mix the order up in this a bit because I'm changing my mind in the moment. I don't want to go too long. I just went to the wrong class. Okay, so let's talk about how this works in general. And so what we have is a region of the brain that communicates to the endocrine system. So in the brain, we have something called the hypothalamus. Hypothalamus, and I'll show you, you don't have to know this, but I'll show you a little picture of where that is in the brain and kind of its relative size. Here we are. Hypothalamus. Okay. Sorry? Yeah, that guy right there. So right in the middle of the brain. That's a nice, I like that picture actually. I'm going to open that in a new tab. But I like this picture because this is an actual brain scan. So if we see there, well, it's that section right there. So that's a real brain scan, by the way. That's a real MRI image. At least I'm assuming that's MRI. That could be a CAT scan. So the thalamus is a region of the brain, and then we have the hypothalamus here, and then we have, we're going to talk about in a minute, these two glands here called the anterior and posterior pituitary, but altogether we just call it the pituitary gland. So this is a section of the brain that is responsible for receiving signals from communicating with the brain. But it secretes control hormones, and it talks to the pituitary gland. And then the pituitary gland in turn controls other glands as well as releasing its own hormones. All right, so we'll talk about that again, but take a look here. So if we look, there's the hypothalamus there. So now it releases some hormones, but the hormones it controls are called releasing hormones, and their job is not to control the body itself, but their main job is to control the release of other hormones. All right, and then when we look at the pituitary, all right, the pituitary gland, on the other hand, releases hormones that control growth, hormones that control blood pressure, hormones that control energy management, the sex organs, thyroid glands, metabolism, but you see it controls other glands as well as causing direct responses. Does that make sense? So it releases what we call control hormones, which stimulate the pituitary gland. We'll write that in words as well. All right, so the hypothalamus is a part of the brain that controls the endocrine system. It releases control hormones. So is this really small on that screen relative to what we're used to? That stimulate the pituitary gland. Which releases hormones that control whole body systems and regulates other glands. And then I will stop writing so you can. I'm not trying to go nuts on you here. All right, take your time, write that down. One more thing I will write. They sometimes call this the master gland. All right, so what are some of the other major glands? We could spend, if we were to Google glands of the human body, you're going to get a monster list, all right? All right, we have the hypothalamus, the pineal gland, the pituitary gland, the thyroid, the thymus, the adrenal glands, the pancreas, the ovaries, the testes in males and females, and lots more. This is just kind of breaking into that. The uterus serves as a gland and releases things. We're not going to try to list them all, but we will. Sorry? Yeah. I actually don't know much about the pineal gland. Never really read about it. Shall we find out together? The pineal gland is a small structure located behind the thalamus in the middle of your pineal. In the middle of these Cleveland Clinic articles are usually pretty good, actually. Pineal body, or the epiphysis cerebri, is a tiny gland in your brain that's located beneath the back of the corpus callosum. The corpus callosum is a section that separates brains. It's part of your endocrine system and secretes the hormone melatonin. Oh, your pineal gland's main job is to help control the circadian cycle of sleep and wakefulness by secreting melatonin. Do you guys know what melatonin does? Yeah, it makes you tired. It tells your body, hey, it's bedtime. Do you know what your circadian cycle is? Sleep cycle. And your circadian cycle is designed to like help you regulate sleep and wakefulness, because our body is designed to have a regular, depending on the person, 6 to maybe 10 hours of sleep. Some people, studies show, benefit from having as much as 11 or 12 hours of sleep a day. What normally helps us regulate that? What does our pineal gland look for? Or not? What's our brain looking for to regulate our circadian rhythms? Thing that tells us day from night. Sunlight. Why do people have more trouble sleeping? And every study shows this than they've ever had in human history. And people do. People's sleep cycles are the worst they've ever been in the history of humans being alive. And that includes holy eras, when people had to worry, was a bear going to come try to eat me while I sleep? Never slept worse. Why? Yeah, so first of all, just speaking like even the last 200 years, we have artificial lights. So it used to be when the sun went down, there wasn't all that much you could do, right? And so you naturally would do what? Sleep. Go to bed, right? Now we invent the artificial light. Well, the artificial light already is going to mess with your circadian rhythms, because you can stay up and do stuff when before there really wasn't that much stuff you can do. Like I love woodworking, right? I woodwork at night all the time. I'll sometimes do it till 3 a.m. and look and go, oh my God, it's 3 a.m. What am I doing? Well, I couldn't do that without artificial lighting, right? Like it wouldn't happen. So I just go to bed and wake up and do it with the sun, right? But the other thing, in addition to all that, now we have all these devices in our house that have light, but that's also interesting and distracting and very glary and blue, right? Like, because even the switch to LEDs or fluorescent lights, it used to be old light bulbs were kind of orangey and sort of warm at least, which could kind of simulate like firelight at night and wasn't that bad. But studies show that like harsh blue lights just keep us up like crazy. And of course, what is sleep cycle correlated to? Well, mental health, intellectual development, physical health. Getting good regular sleep, highly important. All right, so I'm not going to include the pineal gland as kind of the major ones, but I'm going to mention the adrenal glands, the ovaries, the testes, the uterus, and the thyroid gland. Thyroid, adrenal, ovaries, testes, uterus. And I want to use an example here, which is sympathetic and parasympathetic response. Has anyone ever heard of that before? The sympathetic response, the parasympathetic response? Anyone? So this relates to your nervous system, right? So we have the sympathetic nervous system, but it's involved with your endocrine. So the sympathetic endocrine response, the sympathetic endocrine system, is where your endocrine system and your nervous system interact with each other. Does that make sense? So when we talk about the endocrine system, So, for example, when the fight or flight response happens, we say the sympathetic nervous system is activated. I'll come right back to this. I just want to remember how I worded this because I liked it. And I'm going to screw it up. Oh, where are we? Oh, I said I liked it and then I lost it immediately. Hello, where are you? Oh, shoot, that's a different version than what I made. Well, that's fine. I'll just make it now. This results in the release of epinephrine. Epinephrine. Also called, and you already said the name, when you're in fight or flight mode, what's the more common name for the hormone that we know gets released? Also called adrenaline. It does. Thank you. Is that better? By the adrenal gland. All right, and epinephrine is a hormone that is received by a number of different organs in the body. It's actually used in our nervous system as well as what we call a neurotransmitter. You don't need to worry about that, but it acts as a hormone. So oh, this is not the version of that. Well, sorry. There it is. So it's produced by the adrenal glands, and it increases blood flow to the muscles, heart output by activating the sinoatrial node, which is the part of the heart that says time to beat. It makes our pupils dilate, so we let in more light. It increases blood sugar levels, so we'll have more energy. And it does this by binding to these receptors called alpha and beta receptors. Alpha beta receptors are part of these systems that are designed to receive this hormone and then do something in the cell. In the case, again, of the heart, to like get it beating faster. In terms of our muscles, to get them going fast, to get them like ready to go. Again, it increases our blood sugar level. It dilates our pupils. So epinephrine acts to increase heart rate, so it's acting on the heart, increase blood sugar, and does anyone remember what organ regulates blood sugar levels? Did we talk about that? When we talked about enzymes? We did talk about that. Yeah, the pancreas, right? Increases heart rate. That's obviously acting on the heart. Should go without saying. It dilates the pupils. Not dilates, dilates the pupils. That's obviously acting on your eyes. What else does it do? increases skeletal muscle activity. So the release of one chemical can move through the blood, can do all these things at once without the brain having to send individual signals, which is good because the other thing you want to do if you're in fight or flight mode is you want to be hyper aware, right? You want your brain to be busy processing information that comes in, sensory information. Does that make sense? So you might know about epinephrine. Have you ever heard of norepinephrine or noradrenaline? It's the same thing. Norepinephrine. All right, and it's the same thing. It's also part of the sympathetic response. In this case, it has very similar functions. But it's also responsible for reducing blood flow to the gastrointestinal system and inhibits voiding of the bladder and the gastrointestinal motility. In other words, it does a lot of the same things. It increases heart rate and blood pressure, triggers the release of glucose, stores energy, blood flow to skeletal muscles, all these things. But it also, is going to slow down blood flow to your increase blood flow to your muscles, slow down blood flow to your digestive system, help shut your digestive system down. Does that make sense? A second hormone called norepinephrine or noradrenaline, nor just meaning near, has similar function. And constrict and help and signals to constrict and dilate veins and arteries actually. We'll just say blood vessels. To redirect blood flow to muscles and away from the digestive system. It's also a reason why stress can be dangerous. If you're under a lot of stress, your body is often activating your sympathetic nervous system, which means that it's producing epinephrine and norepinephrine, and you're going to do a worse time digesting food, which means you'll get fewer nutrients from it, which might cause us to overeat. So eventually you're going to get those nutrients, and this can cause us to have dysregulated blood sugar, dysregulated weight. It's also very hard to sleep when your sympathetic nervous system is activated because your body is telling you got to be ready for something. You know that feeling? You're lying in bed, you know you're bone tired, but you just can't sleep. Right? Stress has that effect, right? Maybe you've experienced it. Lord knows I've experienced it. So that is your sympathetic nervous system in action. The parasympathetic system serves the opposite function. All right, so it causes relaxation. All right, and a return to normal function. And sorry, we're just going to look this up here. All right, and again, look at all the things it's interacting with. We don't expect everyone to note all these things, right? But I did want to look at the main hormone of parasympathetic response. And again, I usually do this with my cheat sheet that I put there. Okay, good. And the main hormone involved in this response is called acetylcholine. This is just one example. You by no means are totally understanding the endocrine system by understanding just like the parasympathetic response and the sympathetic response. But it's an example that I like because it shows how the whole body can be controlled by the release of just a couple of chemicals. The last thing we're going to write in this note, we're almost done, is we're just going to show that, how that works. And in general, there's two main methods, which is either that they bind on the outside of the cell and then, excuse me, and act inside, or they actually go into the cell and then act in there. But these are a good example because they have big body-wide responses, but also because it's an example of something you see a lot in the body, which is a system that does something and then a system that does the opposite. Does that make sense? So our body needs a way to get oh God, what am I trying to say? If you need something to affect the body to get it amped up, you also need a system to get it calmed down. Does that make sense? Anyway, the last thing I want to show you, I just wanted to make sure I didn't get backwards because again, flying without my usual net here, and I'd hate to write something down backwards, is we're going to write down how hormones work. And there's two broad classes. The first are what we call lipid soluble or steroidal, or the other way to think about them is just highly nonpolar. So we have lipid soluble hormones and water soluble hormones. And here's the basic difference. In the case of a lipid-soluble hormone, we have here the cell. What is this? What am I drawing? Phospholipid bilayer, so I'm drawing the cell membrane, right? And in the case of a lipid-soluble, remember the inside of the cell membrane is these lipid chains, and they are highly nonpolar. Remember that? In other words, they are hydrophobic. In other words, they don't like things that water likes. Does that make sense? So a steroidal hormone, a lipid-soluble hormone, which tend to have these ring structures like this. We'll talk more about that. But here's this hormone. And you don't have to draw this accurately. We'll just draw it there. Here's a hormone. It can pass through the membrane, and there can be a receptor protein inside the cell, and that can be tied right to something that does something else. I'm going to call this a do something protein. In other words, the hormone moves into the cell, and it acts directly on cell enzymes, right? Now, there can still be secondary actions, things like that, but that's how lipid-soluble hormones work. On the other hand, you have water-soluble hormones, and what won't they be able to do? because they are highly polar, the membrane's going to keep them out. Does that make sense? And so in the case of these, their receptor proteins have to be built into the membrane. Right? And then they will often release something that acts on a do something protein elsewhere in the cell. For this course, that's all the detail we're going to go into of sort of how hormones work. Just the two broad categories. You have lipid-soluble and water-soluble hormones. Lipid-soluble hormones move right into the cell. Water-soluble hormones bind on the surface of the cell and act on them that way. So a couple implications. The first implication is that lipid-soluble hormones get absorbed right into the cells. So when we take medication that are essentially hormones, if they're lipid-soluble ones, anything like that, they tend to get right into our cells, and there's a much greater risk of, say, overdose, of them getting in, does that make sense, and staying in. This even goes down to something like vitamins, right? Where your water-soluble vitamins, say like vitamin C, it is very hard to overconsume. You really have to consume a massive amount because these are things that act on the surface of cells and easily can kind of be washed away, and it's hard. They don't persist in our system very long. You can basically just urinate them out quickly. Whereas when you take even vitamins that are oil-based, I think vitamin E, vitamin A, we have to be careful that we don't take more than we're supposed to because they accumulate. That doesn't mean they don't get metabolized and don't get worked out, but we can't just simply pee them out. Does that make sense? Because they work their way into our cells. It's also just neat to understand that like we can have direct action where things just go into our cell and do a job, but we also have these complex systems where we've built a receptor on the outside that says, nah, hey, just come tell me that you want something done, lock in here and say, hey, get going, and then we get action going inside the cell based on this secondary mechanism. Does that make sense? That's it. That's all for today. You could spend a whole career studying your endocrine system. I took one course in endocrinology. It was very interesting, but I'm by no means an expert, and if you saw by how often this lesson I was going to